Each year, Microsoft Research hosts hundreds of influential speakers from around the world, including leading scientists, renowned experts in technology, book authors, and leading academics, and makes videos of these lectures freely available.
Hi, welcome all. It's a pleasure to introduce Jae-woong Chung from Stanford University. Jae-woong is finishing his PhD pretty soon on transactional memory and its applications. And he's done a lot of work on hardware transactional memory and software support for it, as well as applying transactional memory techniques for different applications. And I think he's going to talk about one of those applications today.
Yes. Thank you, Honor. Good morning. My name is Jae-woong Chung. Today I'm going to talk about thread-safe dynamic binary translation using transactional memory. This talk is given at HPCA this year, a few months ago. I was wondering which talk is better to give today, my thesis talk or my latest conference talk, and considering the high technical level of this specific audience, I decided to delve into one issue. So let's start. Dynamic binary translation. I'm pretty sure that most of you heard about it and know how it works. So basically, dynamic binary translation converts binary A to binary B, and when they convert it, they did it as a combination of DBT framework. It's kind of software tool, DBT framework, that provides basic primitives for translation and also analyze application, and DBT tool that performs specific translation. So there are many interesting use cases of dynamic binary translation. First, Transmata Crusoe system is a good example that binary A compiled for platform A can be converted to binary B working for platform B and runtime. And JIT compilation for Java and C++ is another good example. And VMware used dynamic binary translation for virtual machine support. And there has been many proposals how to use a dynamic binary translation for profiling, debugging, security, reliability, and so on. So let me give you an example how we can use dynamic binary translation for security. So dynamic information flow tracking is a very interesting technique for security. It basically tracks the flow of untrusted data in applications. So let's say that we have server applications. We cannot trust all the data coming from the network. And DIFT first receives to tracks the input from the network, and wherever it goes in the application execution flow, it follows the flow. And if later on this untrusted data is used for security critical operations, such as system call, we trigger security exception. So let me give you an example how we can implement this with dynamic binary translation. With dynamic binary translation, we add metadata bits called tame bits. It is 1 bit per memory byte. It doesn't need to be 1 bit per memory byte, but typically 1 bit per memory byte. And we also add yellow instruction in this slide to maintain these metadata bits. And let me walk you through this example. In this example, the first step, let's say that we received untrusted data from the network and assigned it to variable t. Now in this box, we see that untrusted data x is there. We execute the tame bit to set the corresponding bits. And if data bit is flowing to another variable with swap, and next instruction also swaps the tame bits, and the untrusted value is assigned, and tame bit is also assigned. Key point is that tame bit is added, and it follows exactly where the untrusted data goes in application execution. And at the end, if variable U1 and U2 are used for security critical operations, by checking tame bits, security policy can kill this process or trigger security exceptions. So DBT has been working fine and proven its value, and it's been working very good with single-threaded applications. The problem is that now we're in the era of multi-cores, and there will be multi-threaded applications given to DBT as an input. The problem is, how can you preserve the original semantics of atomicity in translated code? For example, let's say that we use dynamic binary translation for binary compatibility, meaning converting binary for platform A to platform B. Platform A provided compare and swap instruction, but platform B we added instruction for compare and another instruction for swap. And single-threaded core, it's fine. Compare and swap will happen one by one. But with multi-threaded application, there can be a race and mix of compare instruction and swap instructions. Another example is, let's say that we added additional instructions to add features. For example, DIFT, we added instructions to maintain 10 bits. And typically what we expect is that this 10-bit instruction is kind of side effect of original instruction. So 10-bit movement happens just in an atomic way following the untrusted data movement. But, it's okay with single-threaded application because the instruction for 10-bit will be executed right after the original instruction. I'm going to give you an example right in the next slide. But with multi-threaded input, there will be some race. So how can you deal with this? Up to now, DBT solutions such as star DBT just doesn't allow multi-threaded input. No multi-threaded input. Another example is Valgrind. It just serializes multi-threaded execution. So there will be only one thread executed at a time.
I have a very high-level question. I don't understand why it is that on single cores, there are no difficulties with multi-threaded programs, because my understanding is that one thread can run for a little while, and then another thread can run for a little while.
Yes. If we just mix multi-threaded input in one single thread, and we don't pay any attention when to context switch out the longest thread, and there will be same problem. Yes, you're right. But what we are focusing here is that, well, in that case, we can deal with it by just paying attention to context switch timing. But with real multi-threaded execution, it's not enough to do that. We need some kind of architectural support or software technique support to deal with the problem. That's the key.
Okay. What does PIN do about this?
PIN about this. So PIN provide. I'm going to go over it. Actually, we used PIN for the test, and it's good. Well, PIN support multi-threaded. PIN support provide multi-thread support for DBT framework itself. So it allows multi-threaded access to code cache. It allows multi-threaded access to trace information. But it has nothing to do with the application code and instrumented additional code that runs with DBT framework. And we are focusing on the code running with, we are focusing on running multi-threaded application code and additional instructions.
How does your model deal with the case where the tainted data affects the control flow?
Tainted, well, it actually doesn't matter for us because, we're going to go back to the case, but what we try to make sure is that whatever instruction there is, even though there is a branch, we make sure that a 10-bit check and branch happens in the same way. For example, if it is not, let's say there is a branch, if it's not taken branch, and there will be transaction, it's way go ahead, but anyway, there will be 10-bit check after the branch, and then if the branch is taken, and then we're going to put checking instruction in the beginning of target code, and then we're going to check it there. Does it answer your question?
Worried about tainted data changing the control flow through your program.
Yeah, still we're going to guarantee the atomicity of checking the bits and then executing the branch bit. And if it turns out to be dangerous execution, and it's the responsibility of implemented feature that takes it. All we guarantee, what the problem we try to address here is the atomicity issue. Yeah,
that's not really what you're trying to address. The model that you're assuming just says, okay, if you change the control flow, that's fine.
So there are points that we have to check security. For example, where do we have to check taint bits? One example is jump address or return address.
Right.
Another example is security. Another example is system call. So basically, if there's a transfer of control flow, we have to check the value. Does it?
Yes.
Yeah. Okay. That's security checkpoint.
I think he's asking, what's your model for DIFT? Because there are many different models. Some people only check move instructions.
Yes.
If your branch is based on a tainted address, then all remaining execution is tainted, and you can't make any decisions about whether or not a security violation has occurred.
Well,
you talk about your model for DIFT.
Yeah, I see. So the point we check is, well, in our experiments, the point we check is any branch instructions and any security system call. That's basically two. There are more minor cases, but basically it's two. Any control flow change and any security call, any system call. That's it. Okay. Any questions? Good. As expected, top audience. Okay, let's move on. So let me show you why it's a hard problem. Again, repeating the problem, going back to the original trace. The problem is, how can we guarantee the atomicity even after we use DIFT to add instruction, and we still expect the original instruction and instrument instruction are executed like atomic instruction, but with multi-threaded input, there will be a race. In this example, this is way watered down example that we actually got from Linux kernel code for directory cache. And they avoided using locks, relying on the fact that swap instruction is atomic, and word granular store is also atomic for most modern processors. So they just executed, but I'll skip all the implementation code. The key is still here. So thread 1 is executing swap, thread 2 is executing word granular store. Doesn't matter which instruction is executed first. It's still lock-free data structure. Now, we did same instrumentation for DIFT, and we added instruction as we've done for single-threaded applications. We added bits, we added instructions, and in the beginning, we have variable t has untrusted data and 10-bit is set. Now, first step, we swap the data, and when we instrumented the code, we expected that 10-bit swap happens right next to the original instruction, and it's going to happen in single-threaded application. But with multi-threaded application, this is lock-free structure, so there can be a race, and store to the another variable happens. From the original programming point of view, it's okay. It doesn't matter. But once we added additional instruction for security, it's going to be a problem because 10-bit is copied following the variable assignment, but nothing happens, and then 10-bit swap happens. So at the end, if variable 2 is used for security system call, and security policy will check the 10-bit, it's not set, system call will be allowed, it's security breach. Again, key point. The problem is, due to the race, there is a chance that expected atomicity from the feature implementer's point of view will break, and then there will be some case that metadata will not follow the original original user data, and there will be significant consequence, such as security breach in this case.
I have one more question. Can you address which classes of memory consistency models would have this vulnerability and which would not?
Oh, in this case, we just assume sequential consistency.
Okay.
Yeah, sequential consistency.
And so which ones would not have this problem?
We didn't study about the other consistency model like weak consistency, because we just stick to that one instruction is executed and all instruction will be observed as it is as a one global history. That's it. Does it address your question?
Yes.
Oh, hopefully. I see some doubt in your face, but we can talk offline. Okay, any other question? Okay. Well, it's atomicity issue. Well, we've been dealing with atomicity issue with locks. Can we deal with it with locks? Of course we can do it. Well, basic idea is simple. Use lock and unlock to enclose data access and metadata access, and that's actually it in terms of correctness. But it turns out that it's going to be really hard to do it to meet the trade-off, good trade-off between performance and programming easiness. First, if we go for fine-grained locking, where we use one lock to have just one original instruction and one additional instruction, there will be huge overhead just to lock and unlock, just to acquire and release the lock. And there will be typical difficulty of using fine-grained lock, such as convoying or priority inversion. But what we found is that the bigger impact in terms of performance is that DBT actually optimized the code after it instrumented new instructions, such as copy propagation, inlining, and register renaming. But a lock and unlock instruction works as if it's memory barrier and it limits the scope of DBT optimization. That's really hurting. And if we don't like fine-grained locking, alternative is obviously coarse-grained locking. But typical difficulty of using locks for DBT is that we instrument all of the code, which basically makes all of the code region as critical section. If we start to use coarse-grained lock for this purpose, I mean, it's easy to expect that there will be huge performance degradation. But hideous thing that I think for this problem is lock nesting. We are dealing with multi-threaded applications, and user application must be dealing with their own atomicity issue with locks. Now we are adding DBT locks to deal with our own problem to address atomicity issue between user data access and metadata access, it's going to be not easy to, in general, prove that there will not be deadlock due to the lock nesting and the order of acquiring user lock and DBT locks.
Would you ever acquire another lock where you're holding a DBT lock?
Well, if we 100% understand what's going on with application semantics, yes, we can avoid it. But typically in our study, it's going to be hard to do it in general.
Okay. If you were, at least if you're using the fine-grained version.
Oh, yeah, no problem, no problem. Basically, if we use one lock for one original instruction and one additional instruction, as you said, no problem. But, you know.
Okay, so you could do coarse-grained stuff, okay, right? Got
Yes,
it.
yes, okay. So, you know, got your question. Good. So the hardest thing to do actually is that, you know, lock programming for the code where all the code is critical section, it's really important to come up with smart multi-threaded program. But if we ask feature implementers such as DIFT implementer for security in the previous example also deal with multi-threading issue, we are asking too much for that people. Well, it's going to be the tool developer, DBT tool developer should be not only the expert for specific feature, but also should be expert for multi-threading. So our solution is basically very easy. Use transactional memory. Transactional memory, I'm pretty sure that most of you have heard about it. So basically, it provides atomic and isolated execution of group of instruction. Atomic, as typical, all or no instruction is executed in a group. And isolation, as typical again. So no intermediate result from the instructions will be exposed to the rest of the system until all of the instructions are executed. So from programmer side, program point of view, just use a transaction to enclose a group of instruction and can just think that that transaction will be logically, sequentially executed against the other transaction and non-transactional accesses.
Is it possible, so you can't put a statement that affects I/O in a transaction?
I/O in transaction, we can do that. There has been an idea how to deal with it. So actually, we will deal with it there. But basic idea is that, for example, one way to deal with it is we defer. The problem with I/O is that once it's done, let's say output is done out of system, we cannot undo it. That's the key point of hardness. Yeah. And one way to do it is defer the I/O until the moment we are pretty sure that the current transaction is going to be commit. That's one way. There can be a case that we cannot guarantee it, and we cannot know that whether transaction is committed or not. Then by system, we're going to force that transaction to commit. Example, if there's any other transaction that conflicts with this transaction, we'll make sure that the other transaction is rolled back.
Well, that's not what I'm worried about. But
Okay.
So if you have a read that has side effects to an I/O device, the read is necessary to complete the transaction, and you can't roll it back.
Oh, side effect that has a right. Yeah. In that case.
But let me finish. Okay, so is it possible that in your system that you have one of those reads in the same area where you've got to do this taint bit checking? So you can't compose it in a transaction because you'll screw up your I/O. But,
Yes.
But since you can't encapsulate within a transaction, you're exposed to race conditions that will allow securitization.
Yes. Two answers. First, in this typical example, we're going to add a transaction to deal with our own issue, and transaction can be as small as containing one original instruction and one taint-bit instructions, so that we don't need to worry about having long transaction that has all complex issues. We can split transaction as small as possible, and going back, well, if we use the transaction to deal with, let's say, DIFT, and in that case, that I/O operation is actually security checkpoint. And then we're going to make, for example, we're going to check taint-bit before the I/O operation and end the I/O operation. We can safely take out that instruction out of the transition boundary. That's another way to do it.
Well, I guess what I'm asking is there's going to be no I/O operation, like for example, a swap in memory mapped I/O space that will require a taint bit to be checked as the next instruction. Is the generator of the taint bit as well as the thing that needs to be coupled with?
Yeah, as long as the data itself we are accessing is in memory, we can data version it. If it's outside, we cannot deal with it. In this case, we make it as outside of transaction. That's one way to do it. If we cannot defer it, if we can defer it, we defer it. If we cannot defer it, we have to take it out of the transaction. Or we can make sure the transaction does not commit. Still, it falls into the case. Whatever side effect it is, the big problem with I/O with transaction is that we cannot undo the side effect. The way we do it is make sure that we don't need to undo the side effect. by make sure that this transaction commits. Any questions? All right. Let me speed up a little bit. Questions? So, well, basically, going back to the point again, programmer point of view, just use transaction to enclose group of instruction and believe that there will be sequential history of transaction and non-transaction access. But underlying transactional memory system runs it in parallel as long as transactions don't conflict. Two transactions conflict if they access the same address and one of them writes. To detect this conflict, every time transaction access new address, we check whether it's read or written and we remember it. And we also make sure that if it's right, we save all the safe values so that we have to roll back, we can restore the memory status. We also check register checkpoint so that we have to roll back, we restore the register values as well. And there has been proposals how to implement transactional memory system, this style of transactional memory system in hardware, software, and hybrid manner. So how can you use transaction for DBT? Basic idea is embarrassingly simple. So if there is a memory access and metadata access, just use a transaction to enclose them. And transaction memory system, by programming as a programming model, it's going to guarantee that these two transactions will be executed in each transaction is going to be executed in an atomic way, but underlying transaction memory system runs transaction in parallel based on the optimistic concurrency control as long as two transactions don't conflict. And it knows how to deal with nested transaction inside another transaction. So basic idea is simple, but the real life ain't easy like that. Well, there are a list of problems that we have to deal with. First, what would be the best way to add transaction? Was it good enough to add a transaction per original instruction and instrument instruction? No, it's going to be really heavy. Transaction begin and end are not free. What if application already have usual locks to deal with their own atomicity issues? By putting DBT locks, don't we break the original semantics of usual locks? That's another question. What if we deal with user transactions and that overlap with DBT transaction? What if there is I/O? We already covered it. Or I/O inside the DBT transaction, we just add it. And the last thing is really tricky. That what if programmers are so smart? So instead of relying on canonical parallel programming primitives such as lock and barrier, they decide to come up with their own synchronization code. And it's hard for us to understand all the semantics. How can we deal with it? I'm going to give you an example. And we also need to deal with the runtime overhead of using transactions. So let's first start. We will go over the problem one by one. First, granularity of transaction instrumentation.
So are you saying the software transactional memory?
Oh yeah. In the beginning, we're gonna give you a result with software transactional memory system, and we're going to also provide the number if we have hardware acceleration in this talk. So the starting point is software transactional memory system. So granularity of transaction instruction. Well, if we add a transaction per original instruction, too high overhead, it's easy to understand. Better way to do it is transaction per basic block so that we can amortize transaction begin and overhead. And some DBT framework provides trace information. You know what trace is? It's multiple basic blocks that happen to be executed back to back, and we can further amortize the overhead. But the problem is that because we are making transaction longer, we will see a higher chance of transaction conflict. So the final version is based on profile, that we start with transaction per trace, and then we observe transaction conflict ratio. If it goes too high, we re-optimize code with dynamic binary translation to shrink the transaction size. Right. So what if there is usual locks overlapping with the DBT transaction? We're going to first consider two cases. One, locked region is so small so that so the transaction locked region is totally falling into transactions, so that locked region is inside the transaction. In that case, to transaction, lock variable is just normal shared variable, and lock acquisition code that sets that sets the lock variable will incur a conflict. So, if there's a two threads try to access this locked region inside the transaction, it's going to turn out to be a transaction conflict, and then we're going to roll back one of the transaction at the point where it tries to acquire the lock. So in that way, we can guarantee that there will be only one thread executing the critical section protected by the lock. This way, we can preserve the original semantics of lock. The other way around, if locked region is really big, and then transaction is inside, and then, well, already lock provided pessimistic concurrency control mechanism and guaranteed that there will be only one thread executing inside the locked region. What's the point of concern? What's the point of running some part of execution with transaction again to provide additional serializability with optimistic concurrency control? That's fine. Don't worry about it. Problem is, what if they overlap partially? And the basic idea is that we cannot do anything about usual lock because it's part of original program. So we're going to split DBT transaction into two parts, two smaller transactions. One completely enclosed by the locked region, the other outside.
Is the assumption on the DBT framework that it provides essentially only per instruction operations, that it doesn't provide any way of kind of adding metadata that spans that spans multiple instructions? And the reason I ask that is because that seems to be is that an assumption of the talk, right? That in the framework you get one instruction, you add some metadata instructions, but you don't ever get multiple instructions at once that you can operate on.
No. If we go for a transaction per basic block, per trace, definitely we're going to have multiple instructions and multiple metadata bit. And actually, that's what we did in the experiment.
So this was really about the semantics that are given to the framework, to the person using the DBT framework. The reason I ask is because I see the appeal of being able to operate, to take multiple instructions in the input and then have a single metadata instruction at the end that executes kind of in an all or nothing manner. But then that doesn't seem to. But then saying that we're going to split transactions whenever it's necessary in order to solve other problems, we no longer have. It seems like there has to be some granularity at which you stop splitting.
Oh, yeah, that perfectly makes sense. Well, in this case, we didn't consider specific semantic requirement of instrumented instructions. We only provide that transition can be bigger to cover such cases, but we didn't actually study how far we can split into smaller part. In this study, yes, you're right. We assume that we can split as small as possible. And actually, the basic size is, with the small size that we used for our experiment is transaction per basic block. Transaction per basic block. That was the smallest transaction size. Okay, move on to the next one. User transaction with DBT transaction overlapping. Well, that's the same story. If they are fully nested, doesn't matter whether it's user transaction and DBT transaction or the other way around. Transaction memory system knows how to deal with nested transaction. If it's partially overlap, again, we split DBT transaction so that one going into user transaction, the other coming out of transaction, user transaction. I/O, we already covered it. One way to deal with the I/O in general in transaction memory system is defer the I/O until the moment that we sure the transaction is committed. Another way is to make sure that this transaction with I/O commits so that we don't need to abort the I/O operations. This actually causes serialization of transaction. It's not good in terms of performance, but at least it guarantees the correctness. Synchronization is tricky. Let me walk you through this simple example. The two-thread and simple instruction, what they try to achieve is barrier. So, thread 2 sets done 2 bits saying that I'm done. And then thread 1 reads the bit and comes out of the while loop. In this way, they have implicit dependency.
I'm sorry for the interruption. I just want to go back to that point. Maybe I'm beating a dead horse here. But
that's okay. I/O, okay.
But you said that the one way to deal with it is to guarantee that it completes. What if you have two transactions on different threads that both get that requirement and they have a conflict?
Then we have to serialize the transaction. Again, it's a serialization, and we make sure that that transaction commit in. That means that we cannot provide another guarantee for another transaction. There will be only one thread executing I/O with that guarantee.
Right. How do you provide that serialization?
Well, by make sure that if there's a two transaction tried to do I/O operation, we're going to just roll that back. So ideally,
if you have side effects.
Okay, even before we execute the side effect, well, somehow we have to detect it first. That's a good question. And when we did an implementation, actually Pin Framework provided an API that to decide whether it goes out or in. And in our application, we didn't see much case of that because it's a multi-thread application, mainly going to memory. But if we can detect it even before we allow side effect, we will make sure that that transaction is going. That transaction is the only transaction with that guarantee in the system, at least for the process.
So you address the problem by not having it in your experiments.
In the experiment, yes, you're right. In the experiment, we haven't seen the problem, but dealing with I/O, you can easily imagine that dealing with I/O is a big issue in general in transactional memory literature, and it seems that they are pretty reasonable to deal with it. And I can refer you to the paper written by Craig Gillis about the analyzing transactional memory system in critical section. Yeah, so dependency goes that way, and executing instruction the other way around. Dependency goes the other way around. This circular dependency guarantees the semantics of barrier. Problem is, if we don't understand what's going on in application layer and just put transaction, we're in trouble. Cause doesn't matter what we do. Transition memory system serialized transition in a way that it executes 2, 3 comes first in the serializable transition history ahead of comes first, then transition 1 and 4, or 1 and 4 before 2 and 3. So ideally, there is no way to serialize these 2 transactions. So it's a problem, and typically in real implementation, it shows up as live lock. 2 transitions kills each other without making progress. So the way we deal with it is to first check that such case happens. The way we detect it is either timeout, and actually what we did is to constantly check whether a specific transaction makes progress or not by checking how many transactions it's rolled back in a row, and if it goes over 5 or 10, and then we say that there is no hope for this transaction to move progress, and we re-optimize the code to make transaction per basic block. And by definition of basic block, once we get into the beginning of basic block, we can finish the basic block where the end is there's a transition end, so that we don't have this internal circular dependency inside one transaction.
So you do this based on profile, basically?
Yes, we observe the abort ratio not only for performance reasons but also to detect this kind of cases.
Can you guarantee that you cover all possible such scenarios?
The important thing is if we go down to the transaction per basic block, we are guaranteed that there will be no dependence, because look at this while loop, the waiting conditions. They actually consist of multiple basic blocks. And the key is this is better. From the transaction memory perspective, as long as we start a transaction and finish the transaction, it's okay. We are making forward progress, right? So if we add a transaction per basic block, by the definition of basic block, we are guaranteed that once we jump in the beginning of basic block, we go down to the basic block, and transaction begin and end will be beginning of the basic block, end of basic block. Okay. Any more questions?
Is transaction the right paradigm to use in this case?
Transaction is right paradigm to use. High level question, open question. Well, that's the reason why I put it as the last one. It's not easy to deal with, but at least we have a case, or we have solution to deal with it. Once it happens, system going to slow down because we have transition per basic block. But the best expression is for greater good. How can I say it? For the common case with the other instructions,
Can't you deal with some other way? Like, why do you have to use transaction?
Basically, we don't want the programmer to worry about finding this pattern and try to use another pattern. We want to make sure that tool developer just add a transaction, and we provide a way to dynamically optimize the transaction size so that even not only for performance, but also deal with these cases, so that from tool developer's point of view, they don't need to worry about finding this case and deal with it as a separate case. That was the key point. Making DBT framework development, DBT tool development easy in reasonable performance degradation. That's key word, I think. Okay, of course, there is a chance to use another mechanism.
I'll defer question.
Good. So we've done with how to deal with how to instrument the transaction and how it interacts with user code. Now let's do the basic baseline performance. We used pin tool with multi-thread support, and we implemented DIFT as a pin tool, and we implemented software transition memory system to begin with, and we used x86 x86 server with 4 dual-core core, and we run the experiment on real machine. We use 9 applications, 6 from Splash, 3 from SpecOMP. In the graph, x-axis is application, y-axis is overhead, where we compare.
Do any of these applications have taint?
Taint? The security vulnerability.
There's no network input on these applications?
Oh, well, in this case, yes, we give you an implementation. Well, actually, it reads from the file. Oh, it's not the network, but definitely it reads from the outside source. It reads from the file, and it reads from the command line. We started tainting from there. But no data book, that's right. Yeah. So it's key. Well, it doesn't matter where it comes from. It's important to check whether it's data from outside or not. Yeah. Okay, good. Any other questions? Okay, so, wow, time is running fast. So x-axis is application, y-axis is normalized overhead, where we compare two things. The baseline performance is DBT framework running with application, and the normalized overhead means the DBT framework, application, and software tools, that software transactional memory system we added. And then we compared the overhead of adding software transactional memory system to deal with atomicity issues. Get this part, the normalized overhead? So,
Did you say it again?
oh, yeah, okay. So, without software transactional memory system, the baseline performance is running pin tool with DIFT implementation and with application here. That's baseline performance, meaning that it's normalized to that execution.
But DIFT normally imposes an order of magnitude overhead anyways, right?
Yes. Well, in our case, well, it depends on application, but in our case, yes. And the overhead comes from using framework, DIFT, application, and software transactional memory system to deal with atomicity issue. And we measure how much overhead we add by doing that.
So 0% is DFT.
This is DIFT. I'm sorry, what is DIFT?
DFT.
Oh, DIFT, DIFT, yes.
So then is the 0% overhead, that's for a system that's incorrect because it doesn't?
Yes, we didn't do anything for atomicity issue. That's
Okay.
baseline. Yes. Well, it's racist, so we can hope that it would run correctly, but no guarantee. Yeah. Okay. So 41%. And in this example, we actually run. Oh, wait a minute. Going back to your question, with the overhead DIFT. Well, I'm sorry, that's the wrong answer. So in both cases, we run DIFT. For the case we measure the overhead, we additionally use software transactional memory system to do. Yeah. So the overhead is not the DIFT. The overhead is software transactional. Okay. Yeah.
That's what I thought you said.
Oh yeah. Thanks. Good. You correct my answer naturally.
So, did you look at the amount of the tainted data that is actually shared between threads? Do you have a sense of that? Have you measured
Yes.
that? Okay.
The way it depends on how you pack the taint bits. It's not only user access shared pattern. It also how you pack the taint bits. So that even though it's different word, it can go down to the one word with taint bits. And in our case, we packed each bit to the byte and pack and unpack it. So even without user level shared access, there is some level of sharing to the taint bits. That's first thing. And yes, these applications for data access part, not much sharing, frankly. But well, we just implemented all over the code. For example, even for barriers and all the other statistics variable. And there, yes, we were able to see conflicts purely due to shared metadata access. And anyway, baseline is 41%. Well, 41%, not that good actually. Not too bad, not too good. So it's time to, but considering the another option that we serialize multi-threaded input totally, executing thread one by one, this is much better. But still, there is a chance for optimization. So let's first see where this transaction overhead comes from. 3 categories basically. First category, to start and end the transaction. We have to take register checkpoint, and we have to initialize transaction metadata. And per memory access inside the transaction, we have to remember which address is read or written by transaction so that we can detect conflict between transactions. And also for the write, we have to remember all the values in the memory so that if we have to roll back, we can restore the memory image. And then, the third type is transaction abort, where actual conflict is there, and we have to undo all the work done by aborting transaction also we have to do specific work for overhead itself. For example, applying the safe value we reserved and then restoring the checkpoint. In our test, this is very federal application that we use, so transaction overhead ratio is really low. It goes down to 0.03%, so we focus on the first two overhead. First, transition begin and end overhead. It's quite easy. Basic strategy is amortize it. So in the graph, x-axis is number of basic blocks per transaction. Y-axis is the same definition of runtime overhead or normalized overhead, and it's obvious, kind of obvious that the longer transaction, the more basic block we have in the transaction, the overhead goes down due to the amortization. Next, per memory access overhead. Well, up to this point in this talk, I just said that to use transaction for DBT, all we have to do is to add transaction begin and end. And it's true for hardware transaction memory system, but it's not true for software transaction memory system. Because we have to let software transaction memory system knows which address is written or read, we have to add software barrier to let software transaction memory system knows the such memory accesses. So we add barriers, and this causes a performance overhead. Typically, two kinds of work is happening in the barrier. First, complete detection by recording the address read or written by the transaction. And second, data versioning overhead by saving the old value when it writes to that address. But this definition gives us two hints. First, if the shared the variable itself is not shared, it's private, and from the beginning we don't do anything for complete detection. And second hint is if this is stack variable, maybe we can just by adjusting stack pointer we can simply just discard any modification done to stack variable. So there can be some optimization chance. So we came up with categorization tree for different memory access types, where the yellow dot will show that we need data versioning for that case, red dot will show that we need complete detection for that case. First, we analyze whether a variable is stack variable or not. If it is, we check whether that stack variable is assigned after, allocated after transition begin or not, begin of current transition or not. If that it's stack variable and stack variable is allocated after transition begin, and we don't need to do complete detection because it's private, we don't need to data versioning because if we have to roll back this transaction, we are going to restore register values, which include the stack pointer. And by restoring stack pointer, we are naturally undoing this allocation of stack variable. So we don't need to remember anything about the modification to the stack variable. But if stack variable is allocated before this transaction has started, and even after we roll back the transaction, stack variable will be still there. So we have to remember if there's any modification to stack variable. If it's stack variable but escapes, or it's not stack variable, we check whether it's private. There are many analyses to decide whether a variable is private or not. For example, in object-oriented programming, we allocate an object with new. At the moment the object is allocated, it's private. And until the moment it publicized through the global reference variable, it's still private. So we deal with it in such a way we find that whether variable is private up to some point. And if it's private, we only do data versioning, but we don't need to do complete detection. By definition, it's private. If it's not private, we check whether it's protected with locks or not in user code. And if it's protected with lock, it is already pessimistically protected by lock, so we don't need to do complete detection. Lock semantics guarantees that there will be only one thread accessing that variable. So we don't do complete detection, we only do data versioning.
Locks are correct.
I'm sorry? That's only...
If the locks are correct in the application?
Locks are...
Just because you see a lock doesn't mean that the variable's not being accessed somewhere else without a lock.
Yes, we believe... Well, the goal here is not to fix the problem of original application. Assuming the original application is correct, race-free, we do this.
Security guarantees.
Yes.
Okay.
Well, I think the best way to answer your question is yes, if implementation requires additional strength of using transaction, yes, we have to admit that. But in this case, we are not adding transaction for security features. In general, we are trying to add transaction to...
Doing optimizations to improve performance. If I did something like add a fine-grained block around each memory access for that address, then I would at least know that my change to taint would be atomic with the access to that address.
Mm-hmm.
But you're making an assumption here about the user level locks.
Yes, user level locks.
Performance,
Oh.
which might be breaking taint analysis.
Yeah. If I just stick a lock randomly in one of my threads, that won't make my program incorrect if the lock doesn't need to be there. But now I'm exposing myself to races on the taints.
Yes. Oh, the important thing is,
Is that what you're saying?
yeah, the important thing is we have to distinguish two things: race with the user data, race with the metadata. This categorization tree has nothing to do with metadata.
Right.
It's only for user data.
Yeah, we get that.
Yeah. So still, that's the reason why you have to still do data versioning. If, let's say, that this fine-grained locked region that you said is inside a bigger transaction, and for this specific access to the shared variable, we don't need conflict detection. But there might be a conflict due to the metadata right next to the original access, and there will be conflict. We have to detect it. We have to roll it back. For the rollback, we still have to do data versioning. But conflict detection, no. It is guaranteed that there will be only one instruction. Does it make sense? Okay, fine. So, well, all hope's gone, and we have to do both things. We have to do both data versioning and conflict detection. The key point of here is that anytime we cannot analyze specific case, we go to the right side to be on the safe side. We just give away that optimization chance and go to the right side to be on the safe side. So we didn't explore all the chance of doing software optimization, but we tested several cases. So with stack optimization, overall go down 36%. With binaries, it goes down to 34%. And we did additional optimization, and it goes down to. Splash. Yeah, Splash 2 application and Spec 1P application.
Is the original Splash 2 from like how big is your working set? These the original
Yes.
2 megabyte working set.
Data size.
And the original Splash 2 is for itty bitty, right?
I
This
don't
was 10,
quite.
15 years ago.
I say when I used it in my thesis, the machines were so small.
Yeah, that's what I'm saying.
Yeah,
Did
yeah.
you do any effort to scale these up for today's computers?
Well, frankly, the way I did it is I increase the data set as long as it runs one day. This is not with simulation, so it's, what was it?
How did you choose these rather than running a traditional DIFT application like a web server or an FTP server? Or
The reason is that those applications are more vulnerable for security, but our key point is to eliminate the race. In terms of sharing data, those applications are embarrassingly session parallel. So there's big.
The applications that care about security don't exhibit this problem.
Yes, that maybe I entered the confusion by using security example. I just use it as an example how to use DBT and what kind of problem there can be. But from our perspective, we are more interested in races. So, and this shared application, by definition, shares variable, pushes our system further. Stress, yeah. So, anyway, the basic idea is after we submit this paper, we did additional experiments, and with software optimization, it can go down to 30%. You're happy with 30%, move on. But if you're not happy, we start thinking about adding hardware support. From here, we did simulation work. So we compared basically 3 types of hardware acceleration. One, STM Plus that has hardware acceleration for register checkpointing, one instruction, and gradually, even though in the implementation. Okay. And hybrid TM, where it provides hardware support for register checkpointing and conflict detection. So we remember read set and write set, it hardware bloom filter and check the conflict. And the third type is full hardware implementation, where everything happens in hardware. So the quick summary is application normalized overhead again. Quick summary with STM Plus, overhead is 28%. With hybrid TM, overhead is 12%. With full HTM, overhead goes down to 6%, which is pretty good. But, well, comparing this 12% and 6%, half of overhead is gone. But from total execution time point of view, 6% is not that impressive. So we are definitely seeing some kind of diminishing return. And maybe for transition, to use transition memory system for DBT, hybrid approach makes sense.
So this is overhead over the base case, which was with the DIFT on top of the so how much of the actual non-DIFT execution time? In other words, if you took the base case to be without DIFT at all, how much?
What is the overhead of DIFT itself?
Yeah.
We actually didn't measure it. The reason is we don't care about how efficient DIFT itself is. Well, we care about once such implementation is there, how much overhead we're going to add to deal with the atomicity issue. That was our key point. So, yeah, but it's interesting. Yeah, question. Any other question? Okay. So, done. Wow, it's done in time.
All right,
Okay.
since we're done. So does DIFT affect, I suspect the answer is no, but does DIFT affect multi-threaded applications worse than single-threaded applications?
DFT effects. I didn't get your question, meaning worse in terms of performance.
Yeah.
Of course, because multi-threaded application and single-threaded application, well, without worrying about atomicity issue, they just instrumented the same way for multi-threaded application and single-threaded application, and that's the same. It's because the same idea. Well, forgetting about all the conflict missed issues in the multi-threaded application. Well, basically, DIFT, without worrying about atomicity issue, DIFT just added.
The number of, so let's say I parallelize my application, the number of processors at which performance is optimal or highest, does that number change when I apply DIFT, do you think?
I think it depends on how you pack metadata bits shared by it. So typically, up to now, in DBT papers, they pack that 1 bit or 8 bits, all 8 bits per byte, so that they minimize the memory footprint. Because it's single-threaded, mostly the study is done with single-threaded application, no reason to worry about atomicity issue. Right. But in our case, it will hurt, because actually it's going to be shared by multiple threads and conflict miss between the cache coherence.
I'm not sure if I missed that, but how do you handle pointers to tainted data and pointer aliasing issues?
Point of aliasing issue.
Yeah, you have a pointer to tainted data, and then you alias that pointer, and then dereference that?
Well, it doesn't matter whether in application level it's aliasing or not. What we see is the eventual memory access. So in the program, there can be a point aliasing while variable A eventually turn out to be variable B and variable accesses it. It's hard for compiler to understand it. But in transition memory system point of view, it's just normal load and store instruction. We don't care how it is explained in original source code. Questions? Okay. Wow, I drew this tough audience with this talk. It's great. Any question? I'll be happy to talk with all after this talk. And I guess that's it, right? Let me finish. Okay. So quickly, multi-threaded executables are a headache for DBT. Well, we use transaction to address atomicity issue. Baseline 41%. With software optimization, down to 30%. With hardware optimization, it can go down to 6%, but pay attention to diminishing return. Hybrid approach makes sense in terms of trade-off between performance and hardware cost. That's it. Thank you.